Welcome to the 19th lecture in Physics 10 in 30 lectures. In this second lecture of the week, we cover electric circuits and some homework questions from chapter 9. We start by introducing electric current and a demonstration of Ohm's law. We also try developing our intuition for electric current through water flow analogies. And we look at some of the chapter 9 homework questions involving calculations in the second half of this lecture. As a reminder, in the older recorded lectures, the chapter and section numbers in the video are shifted from the chapter and section numbers in the LibreText version of the textbook. When the video says chapter 10, we are actually looking at chapter 9 questions. Let's start.
By the time we started talking about voltage, that should have started sounding more familiar because you see the word voltage around in everyday life. And what we are really leading up to is this. Here is a paradox that you probably have seen before. This is a light bulb. And this is, I guess we call it power supply. But what it really is it's a voltage supply. You see volt written here. So I have these knobs that I can control to increase the voltage that I'm applying to this light bulb. And when I increase it enough, you see it there. And when I increase it enough, you see the light bulb start to light up. Like, how many, everyone here has seen the light bulb light up? So this is what we are getting to today. What we are covering now is something called the DC circuit. So I just want to remind you what we have been talking about in static electricity. So what we've been talking about in static electricity, it particularly has to do with what we said about conductors. So for conductors, what do we know about behavior of conductors in static electricity? Like, what are some of the conductor properties you know? So the definition of conductor is that, so you could call that definition that electrons or the charges are able to move around. So charges are able to move around. But in terms of problem solving, there were at least 3 properties of conductor that we covered. 2 of them are kind of important for you to remember. So, we do start off from the fact that inside the conductors, charges can move. That's the definition. But when you're doing electrostatic problems, you kind of have to know the properties of conductor beyond the definition. Of course?
Electric field is 0?
Yeah, that inside electric field is 0. What else? Yeah, so also inside, voltage remains the same, or another way to put it is change in voltage across conductor is 0. Right? So this is what we have said about conductors so far. And I can't emphasize enough that these properties that we have talked about, it applies for static electricity. Because the way we got to these properties was that we were assuming static equilibrium. That's where we use this definition. If it's a static equilibrium, then charges inside the conductor cannot have any forces on it. That's why electric field was 0, and so on. So the reason I'm highlighting this is now we are going to move beyond this assumption. We are going to move on to situations where this assumption will fail. So let me do this quick demo. So I have this long conducting wire prepared. Let me just pass around the little segments of the same wire material. I found this roll of, oh, you guys probably can see. Roll of wire, just pass it around so that everyone can see what it is. Pass this and pass it to the center, please, so that people can see it. I mean, it's just a regular piece of wire. There's nothing special about these wires. I had 3 prepared, but I think I dropped one of them. Anyways, while it's going around, so it's just a regular piece of wire. I think it might be made out of steel because it rusts. I was just sandpapering off of the rust. So this is a piece of conductor. And normally what you do say is that because this is conductor, voltage difference from one end to the other end of the wire is 0, according to what we have said. And even with this power supply, you can kind of see it. Let me actually set up some of these settings for safety purposes. So I'm going to light up this light bulb. And I'm just touching the second knob to do something that I'll explain later. Wait, I might, yeah. I have to set this for safety purposes. All right. I'll explain what the second knob is doing. All right, that's good enough. All right. So what we say about conductors, it holds most of the time. So I have this power supply, these two wires connected to the power supply. Right now, the voltage between these two, it reads 6 volts. That's what you are seeing on the screen over there. Thank you. Everyone got to see the wire? Nothing special. Right now, it says 6 volts. So what it's saying is that there's a voltage difference of 6 volts between them. Now, when I allow these conductors to touch, by the way, don't do this too often. It's don't do this with regular battery, please. This power supply has a safety feature built in, where it is actually safe for me to do it. You do see a little bit of spark. When I do this, sometimes you see a spark. But so, when I allow these conductors to touch, then there's 0 volt between them. Well, close enough to 0, right? So this is what we have been talking about, that conductors are, that defines equipotential. But when you set up a particular arrangement, sometimes you don't see 0 volt between two ends of a conductor. So let me connect one of the wires to this end here. So wire connected here. Now let me wrap it around for good measure. And so right now the other end is not connected, so it's reading 6 volts as you might expect. But when I connect this at this end here, oops. Now it doesn't quite read 0 volt anymore. It's reading 0.4 volts. And in fact, how many volts it reads, it'll depend on where I place it. Let me take this length of the wire, take about half its length, and this is about half its length, and connect it here. It was 0.4 volts before, right? When I connect it here now it's 0.2 volts. Now let me do one more thing. So let me take the same length of wire, but connect it twice. So double up the wire. So connect this end to this here, and connect the other end, same length as before, here. And this time, well, it's somewhere between 0.2 and 0.1, because it's flickering between the two. So you get, so how much voltage that I'm reading at that other end, it depends on the exact arrangement of this wire. So this is the type of situation that now we'll start to deal with, that does not, where the assumption of static equilibrium doesn't hold anymore. So let's try to describe exactly in what way it's not a static equilibrium anymore, and what that means. So let me call this intro to circuit. So let me draw a picture of this conducting wire, because this wire is so thin, let me draw it a little bit bigger. So imagine this sort of cylinder is a representation of the conducting wire. So what we do by connecting these leads from the power supply to the conducting wire is that we are applying a voltage across this conductor. We apply a voltage at this end, called, let's say, voltage of 0 volts. Sorry, I'm using V in too many ways. Well, I'll use this stylized V when I'm in volts. And let's say at this end, I'm applying voltage of, let's just say 10 volts, so that we have some specific number to talk about. So if this wasn't a conducting path, if there wasn't this conducting path between them, what would this mean? Having 0 volt here and 10 volt here. Like imagine that instead of this being a conductor, imagine this was like the capacitor setup, where I have a plate on the left that's charged to 0 volt, and plate on the right that's also that's charged to 10 volts. Like if there wasn't conducting path, what would putting this voltage difference mean? There's electric field between these two. How was that electric field set up? Oh, in fact, let me draw the electric. What direction would the electric field go? To the, let's see. To the left, right? Yeah, okay. Yeah. From high voltage to low voltage. So it would mean there's some kind of electric field between them. And why is there electric field between them? I mean, you could say it's because there's voltage difference, but so that there's a third feature that having this voltage difference involves.
Charge separation?
Yeah, there's a charge. On this positive plate, there should be some positive charges here. And on this negative plate, there should be some negative charges here. And so that's the electrostatic picture. When we are now dealing with a circuit where it might not be at static equilibrium anymore, what we are saying is, all right, instead of these two being separated, now they are connected by a conducting material. And I want to look at what should change now that these two ends are connected by a conductor. So this is where you have to have some constraints given to you. So, in static electricity, essentially what we said was, if we are dealing with static electricity, what we would say is that this voltage is not a known quantity. Now, initially there might have been 0 and 10 volts. Initially there might have been negative and positive charge separation. But in static electricity, what we say is, well, after this initial setup, we are going to remove our hands, let whatever happens happen, and then look at it again when everything's have come to static equilibrium. In other words, we are saying we are not going to apply voltage anymore. Let's see what happens. What would happen is negative charge and positive charge will attract each other. It'll be on net, neutral all the way throughout, be at 0 volt, have 0 electric field. Like that would be the situation, right? So that's what we did in static. Whenever we are dealing with a static equilibrium, now we are changing the terms. Now we are saying that, no, we are going to continue to apply 0 volts and 10 volts at these two ends. And that's kinda what we are doing with this. In other words, let me change the numbers so that it actually, what I'm saying in words matches physically what I can make happen. So let's say with this, I'm trying to apply 0.5 volts. And let me fiddle with the second knob a little bit. And what we are saying is that, so now there will be situations where if I'm trying to apply 0.5 volts, I can't. Physically, I'm just not able to apply 0.5 volts. But in circuits, what we want to deal with now is deal with the situations where the power supply is trying to supply 0.5 volts, and the rest of the setup is set up in such a way that the power supply is able to. Move this. Power supply is able to. So I'm trying to apply 0.5 volts between these two ends of the wire, and I can. So that's the situation. So that's the change in condition that we are now doing. So before, what we said was, it's the static equilibrium condition. This is what we are holding true, that charges don't move. When we get to circuits, Now we are getting rid of that, and we are holding something else constant. And depending on the problem, this will change. But for this initial discussion, let's say we are holding change in voltage, difference in voltage constant. So here, what we are doing is we are doing what we needed to do to maintain this voltage difference. So if we have the same voltage difference, and we have this electric field, that must mean that we still have this charge separation. Because without this charge separation, then how will we have electric field? I mean, to have non-zero electric field, I must have some charge accumulation somewhere, right? Now, what happens with these charges? Like, imagine what happens in the next moment. Do these charges just remain where they are, or do something? Let's say the positive charges, they don't move. They are protons or whatever. What happens with these negative charges in the next moment? They move, right? So these negative charges, they will feel force from this electric field. So they will actually start to move this way. Negative charges will start to move to the right here, right? In other words, you are losing negative charges here. And that also means you are actually losing positive charges here also. Because when negative charges finally reach this end, then by that same amount, this end is that much, it has less net charge there. Okay? So so there must be something that we are doing to continue to maintain this voltage difference and continue to maintain this electric field as we are losing these charges. Guesses? There's a supply of charges that's coming in. That's really what this power supply is doing. So if I was measuring voltage difference at this end with another voltmeter, then the moment I turn off the power supply, the voltage difference will go to 0. The moment the power supply doesn't supply charges anymore, it'll go to 0. So to maintain this setup, there must be a continuous supply of negative charges that are coming in to replace the charges that are being lost as they move from one end to the other. And here, there must be continuous sort of extraction of these negative charges from this end, so that as negative charges come in, they don't make this end net charge 0, that this end remains net charge positive. So there has to be a continuous flow of this charge here. And this flow of charge here is what we refer to as current, or electric current. And so this is now what we need to explicitly deal with. You can look at it this way. When we said in static electricity, assuming static equilibrium, another way to say the same thing is to say the current movement of charge is equal to 0. That's what we were assuming before. And now, as we get to circuits, we are going to say my current, it might not be 0. In fact, it's definitely not 0 in a situation like this. So I probably should define current. And I want to define current in a careful way, because this is something that you will see a lot. And depending on what reference material you're looking at, you might even see something like this. I is equal to dq dt. And I try to never write this down without there being some sort of explanation. Because I think it's important for you to know exactly what we are measuring here. So with the current, we are trying to measure a flow rate of how quickly the charges are flowing. How do you think we should measure it? What's some, I don't know, reasonable, let me put it this way. In what unit should we measure current?
Something similar to voltage.
Well, it might relate to voltage, but we will eventually relate it to voltage, but not right now. Right now, all that voltage is doing is that it's just maintaining this. So there being this voltage difference, it's just saying that something is being done from outside to maintain this charge separation by continuous flow of the charges. So this is what I'm imagining. Imagine you are, imagine you are a little observer standing here, looking at all these charges flowing. And the other ends are so far away that you are not going to be able to see it. You don't really see any voltage difference. I want you to describe, okay, as an observer standing here, what can I measure to see what my current is? Or let me put it this way. So the most useful analogy to build up your intuition about electrical current is when you say the word current, what else do we call current? Can you tell me other words that are not electrical current, but would be used with a noun current, not the adjective current? Right, river current. So this word reminds you of river current or ocean current or whatever. In that context, what does the word current refer to? Flow of water, right? So that's what I want you to imagine here. So here I was drawing the picture of electrical things, but if you imagine this as just a water pipe, and there's water flowing through it, then that would give you a useful analogy to electrical current. So I want you to think of measuring this electrical current as, well, we want to measure it the exact same way we would measure water current. So if you have water current, in what units do you think you would measure water current in? Okay, so there are different ways of measuring water current. So imagine you have a pipe here. So I think what Kevin was trying to say was you were describing the water velocity. As in, imagine this is filled up with the water. Then if you are tracking a little section of this water here, you can imagine dropping a little bit of ink droplet and see how fast it's moving. And you are trying to measure some flow speed. But that doesn't actually tell you how much water is flowing, because this rate can be really high, but the water pipe can be so narrow so that not much amount of water is flowing. So when I talk about the word flow rate, really what I'm interested in is with the total amount of water that's flowing. So how would you, in what units would you measure the total amount of water that's flowing?
Gallons per hour.
Something like gallons, some unit of amount per time, right? So flow rate, so it would be, denominator would be second, and the numerator will be something that indicates how much amount. It can be volume, like gallons, or if you're trying to keep to SI units, it might be kilograms if you're doing it by mass, or if you're doing it by volume, it might be cubic meter. So that's how we measure flow rate with any fluid. And I want you to separate this flow rate from the flow speed. It's two different things. And it's the same thing with the current here. So with the current, mainly what we are interested in is the flow rate. So how much charge is flowing in a given amount of time. So the unit that you should measure current in is, it's going to be in coulombs. Amount of charge, unit of charge, right? It's going to be measured in coulombs per second. So how are we counting the amount of charges? So this is the unit it's going to be in. But let me actually describe how this guy would actually measure current. So Miguel, when you said you measure flow rate in gallons per hour, how do you measure the gallons per hour?
You measure how much water travels from one location to another location throughout that period of time.
Okay, one location to another location. So this is a picture I can kind of imagine doing. Here's a water reservoir here that you are drawing water out of. And here's the here's the water reservoir at this other end that you're putting water into. And what you're saying is, you look at, all right, how much water this has lost, and how much water this has gained, and it would be the same amount. And if you are saying that your flow rate was 1 gallon per hour, then which is very slow, then in 1 hour, you would have seen this rise by amount of 1 gallon, right? That's what you're saying, right? Now, I want to change the description of this in a way that I have a local description. As in, so here, I had to look at the entire picture globally. As in, I had to look at how much was lost here, how much was gained here. I mean, they're going to be the same. But I had to kind of look at the entire system. I want to come up with a way of measuring this so that I can actually look at a single point. The way your meters are set up, both the water meters and the electricity meter in your house, it's set up at a single point. Like a meter doesn't have access to anything else in the house except a single point it is. So I want to describe how we measure flow rate. If all we have access to is, let's say, a single point here. So at this single, well, I say point, but this single cross section, let's say that's all I have access to. How would I measure flow rate?
You imagine how many particles would pass that given line during a period of time?
Yeah. So it's a really simple measurement. It's a simple measurement. How much? So this is the picture I want you to imagine. Some amount of water, which is all flowing at some speed. Now some of them will cross. Let's say all these represent movement of water in 1 second. Some of these cross, some of them don't. But as someone, I guess you could think of this like a toll gate. As the toll gate keeper, he can measure how many of the water crosses, how much doesn't. Amount of water that crosses this point is what gets counted into this 1 gallon. Amount of water that doesn't, either because it's already on this side or because it's too far away on this side, then that wouldn't get counted. So when we talk about electrical current, the qualitative description of that is number of charges per time. But I want you to be careful what we mean by number of charges. And the number of charges is, imagine that this guy is setting up a toll gate here, sort of a single plane that goes through this material and has the cross-sectional area. And what this guy is counting is in 1 second, how many charges are crossing over from one side to the other side. That's all he's looking at. So when we say number of charges, it's the number of charges that, let me call it cross checkpoint. That makes intuitive sense? All right. So that's in this expression here, that's what's meant by delta Q. How many charges are crossing the checkpoint? Now, let's just make the numbers concrete. In this picture, let's say over a time of 1 second, you measured 1 coulomb of charges crossing across this boundary. So you are measuring current of, right now, 1 coulomb per second. There's actually a unit for this coulomb per second. That unit is, in that SI unit for coulomb per second, you can describe this as 1 ampere. Ampere is the unit of current that we will deal with soon. And that's actually, well, that's why this says AMP. It's for ampere. So the second gauge here is actually measuring current. And the second knob is setting the maximum amount of current that can flow. So I want you to think about the second thing that we might consider changing, and see if anything real changes. So this is observer A that was measuring current at this point. let's say someone else sets up an observation point at some point later. So I have an observer B who set up another checkpoint here and measures current here. How do you think current at point A? So the symbol we use for current, by the way, is I. That's why it's I here. I don't know why it's I. It's just I. Let's say current at point A is IA, and current at point B is IB. From knowing current at point A, do you know anything about current at point B? Katie, what do you say? How are these two related? That they should be the same. Yeah, they should be the same. If you don't have that intuition, I want you to fall back to this model here. So let's say you can measure current flow rate of the water here at two different points. You could measure it here. See how much water is entering. Let me call that flow rate in. Or you can measure it here. How much water is leaving the volume, flow rate out. So hopefully more of you have intuition that this flow rate in and out should equal. But why are they equal? Like, why couldn't there be more water entering in here than leaving?
There'd be like a bunch of water accumulating in the middle.
Yeah, that would mean because mass is conserved. If more water flows in than out, that means the water is accumulating in the middle. And one of the properties of liquid is that they are really hard to compress. So to a very good approximation, amount of volume coming in should equal amount of volume going out. Because it's so hard to compress them that whatever comes in has to mean something gets pushed out by the same amount. And it's the exact same thing with the current, exact same thing with the charges. However many charges are coming in at one end, it turns out charges are super hard to compress. As in, if you try to accumulate even tiniest amount of coulombs of charge in a wire like this, it involves such a huge amount of voltage and force that you just can't do it. So the very good approximation to make is that there's no significant charge accumulation anywhere here. So what that means is however much charges are coming in here, exact same amount of charge has to go out here. So this is another useful thing to know about current. Even though we define it with reference to a particular checkpoint, where the checkpoint is actually doesn't matter. As long as you haven't broken off a branch so that charges can go elsewhere, checkpoint can be along anywhere along a single branch of conductor. Okay? Let's say we defined all the current, we defined it as some amount of charge flowing through past a point in some amount of time. And now what we want to do is, so as you saw in the demonstration, the way we got current to flow is by applying a voltage across a conductor. So I want to describe the experimental law that tells you how that happens. So this is the law called Ohm's law. And at least until I get tired of it, I'm going to put quotation marks around the law. Because Ohm's law is an exception to the fact that most of the actual laws you see in this class, they are fundamental laws. There are no exceptions. There's no exception to Gauss's law. If you ever see me say in a multiple choice question, say that this is a rare exception to Gauss's law, well, that's a false choice. Ohm's law is exception in the sense, it's not really a law. It's more of something that happens commonly. So let me demonstrate to you the situation where it happens commonly and see what the law says. So I'm going to turn this back on. And for safety's sake, what I'm going to do is I'm going to turn the voltage way down to 0. And this current control knob, I'm going to turn it up so that this power supply is not going to try to limit the current. I still have these two ends connected. So there's a current flowing through this conductor here as soon as I start applying voltage. So let's see what happens as I apply voltage. So I apply a little bit of voltage here. Let's see, when I apply about 0.5 volts of voltage, difference from one end to the other, then I get current of 0.22 ampere. Let's keep going. Let's try doubling the voltage from 0.4 volts to, where do I look at? 0.8 volts, 0.37. I think I can probably go as high as 1.5. So let me, so that it's easier to see, let me go from 0.5. So at 0.5 volts, it was 0.22. Let's go to 1 volt. At 1 volt, it's a 0.44. And let's go all the way to 1.5 volts, 0.66. What do you think the relationship between voltage and current is? Proportional, right? Yeah, that's what Ohm discovered, that this law holds with most conductors. Now, the reason I keep putting quotation marks around the law is that it's not universal. There will be materials that don't obey this law. But so to draw that distinction, we say for ohmic materials, as in materials that obey Ohm's law. It's sort of, self-explanatory, right? And what ohmic material, it includes a lot of different things. It includes most conductors. And in fact, it might include all the conductors, because the things that don't obey this are like semiconductors. And sometimes when the conductor's temperature changes a lot, then it can be considered non-ohmic, in the sense that the relationship isn't strictly linear. But so for materials that obey Ohm's law, essentially most conductors, this relationship holds. The voltage you apply is proportional to the current that you get. So we want to go a little bit past this proportional relationship. So what do you do when you want to go beyond simply saying one quantity is proportional to another quantity? Like at the very beginning of electricity, we wanted to go beyond simply saying that, so we could have said that electric force is proportional to charge, a product of charges divided by distance squared. But we wanted to go beyond this. We want to say it's equal. What did we do to make this relationship equal instead of just merely proportional? Yeah, we introduced a constant here when we are dealing with electrostatics, so that we can say this is equal to this. And we'll determine the constant later. So we are going to do the same thing here. With the Ohm's law, what we really want to say is we want to say that voltage is equal to some quantity involving current. So the constant of proportionality, this is what we are going to call resistance. So this is a new constant that we are introducing. It's what we call resistance. And it's a property of the object that you are dealing with. Not property of material, property of the object. I will demonstrate what I mean by that. But this is probably a good point to pause a little bit and talk about the units. So the unit of voltage is in volts, right? We've talked about that at length the other day. Unit of current, we just introduced it today. Unit of current, or coulombs per second, that's in amperes. That's the new unit of current that you just heard today. So resistance also gets its own unit. There's a name for it. So unit of resistance, it's called ohm. That's the name of the unit, because it comes from Ohm's law. And the symbol that you are going to see for ohm is not O or capital O. It's actually capital omega. I don't know why. I don't think we are using capital O for anything, but I guess it's too confusing with the zero. So capital omega is what we use for abbreviation of ohm. Now, what do you think 1 ohm is in terms of these other units you have seen? Like, what is 1 ohm in terms of ampere and volt?
Volts per second per charge, volts per second divided by cooling.
Okay, volts per. So why do you put volts on the numerator?
I was dividing it by current.
Oh, I see. You are imagining solving this for R. You can do it that way. So if you are solving Ohm's law for R, take it as a, defining the resistance R, then you would say R is equal to V divided by I. So the unit of ohm would be unit of voltage, volt, divided by unit of current, ampere. So you could say that 1 ohm is equal to volts per ampere. And as I said the other day, the units for electricity kind of can get complicated in the sense that there are a lot of interlocking relationships. So I would just stop here. And if you want to express it in terms of coulombs and other basic quantities, then you can, but I won't. You can convert volts to joules and whatnot, and you can do that. I won't. So this is the definition of resistance. This Ohm's law relationship is how we define resistance of anything. But I want you to notice something here. So resistance of this entire wire is some amount. In fact, I think we can actually measure it. So let me put this at some reasonable value here. Let's say, let me put it at, let's see, where is it? I don't know if I can get as high as 1 amp and not anything bad happen. Let's just try that. All right, that's good. If it gets hot, I just won't touch it. Yeah. If you start to see anything burning or glowing, tell me. All right, close enough. So this piece of wire, you can say that it has resistance of, we are just measuring that there, right? So volts per current. So the resistance of that wire that you see is equal to 2.3 volts per ampere or 2.3 ohm. It's actually a pretty small resistance, which makes sense. It's just a piece of wire. Now, what I am going to do is, let me turn this off first. I don't want to hurt myself. Is it hot? All right. Voltage-wise, it's actually pretty safe. What I'm worried about is that this might have heated up, and I don't want to burn myself. So now what I'm going to do, it's still the same piece of wire, but I'm going to change my arrangement a little bit. Instead of using the entire length of wire, I'm going to use half as much length of the wire here. What do you think will have happened to the resistance?
It would double.
Resistance would double or half?
All half,
Yeah. So, you have some sense of what this R means here, right? The name says resistance. It resists current. And you can actually, the higher the R is, the more voltage you will need to put through the same current. So this R does measure resistance to current. The higher the R is, the lower the current you have if your voltage is the same. So here, before I got 1 ampere to flow with 2.3 volts applied. I'm still going to be applying the same amount of voltage. Let's see how much current flows now, assuming I don't break anything. Did I break anything? All right, yeah, I'm starting to break something. So 2.3 volts, it's not quite double. So it's probably easier to see this if I, it's actually gonna be hard. As I keep saying, this is a pretty low resistance. So what the resistance of half wire, what it's supposed to be is half of this, approximately 1.2 ohm, which means, let me actually do it this way. So having turned it on, let me reduce the voltage until the current goes down to 1. So right now I see 1.4 instead of 1.2. And that small difference is actually amount of resistance in this wire. Because, as I keep saying, this is only a piece of wire. It's not some specially made resistor. So I made the length of this thing half, but what you have to keep in mind is that I have these other wires here. So there's something like maybe 0.2, 0.5 ohm of resistance in the rest of the system. But you kind of see here that when I made the length half, the resistance went down to about a half. So when you are looking at the resistance, the quantity that we measure in ohm, it's the property of the object. It's a property of object. So in terms of hearing that this wire has resistance of 2 ohm is as useful as you hearing that this mass has mass of 500 grams. Good, if you want to use this to do something. But if you want to record this in a table for other engineers to look up, that's not useful at all. Like, why do I care that this object has mass of 0.5 kilograms? Why do I care that this piece of wire has resistance of 2 ohm? Like, I don't care all that much. So in order to describe property of material, this is made out of steel or iron. You want to know the property of the iron. And there the idea we use is an idea called, the term that we use to refer to this idea is the phrase resistivity. And what I want to get at right now is the relationship between resistivity and resistance. So what's the symbol for? A symbol for resistivity is rho. Right, that makes a lot more sense. So once again, don't confuse this with the charge density rho. It's just a symbol for resistivity. So what I want to get at is some relationship between resistance R and resistivity rho. So you guys already got at a part of it. So this is the same material. Let's say we keep its material property constant. Then what you said was that the relationship, this is as far as we got. So resistivity and resistance, they should be proportional in the sense that all else being the same, if the resistivity of the material is higher, maybe I use something that has higher resistivity than iron, then the resistance would go up. And what you guys got at intuitively was that resistance is also proportional to the length of the material, right? Because intuitively, your intuition says that if I have a longer material, then there's more like things resisting flow of charges. Should that be it, or are there other things that resistivity might depend on? Yeah, cross-sectional area. So let me do it this way. I'm going to double up the cross-sectional area by doubling up the wire. So let's connect it and see what the resistance of this, the doubled up half-length wire is. So what we said before was it should be about 1.2 ohm. The actual measured value was 1.4 ohm. At some point, it's going to be harder and harder to measure because I'm going to get too close at the rest of the system. So, but let's just try it and see what we get. Turn it on. Let me, did I break anything? Okay, not yet. All right, so, understanding the huge errors involved in measuring here, my resistivity, so how do I call it? Let me call this resistance of half wire doubled up. Is about 0.8 ohm. Or, if you imagine the number I was telling you before, that the resistance in the rest of the system is like 0.4 ohm, then from this, using the same length, it went down about by half of what it was. So yeah, it's inversely proportional to the area. The larger the cross-sectional area, the smaller the resistance. So this is the relationship between resistance and resistivity. That this is the resistance and this is the resistivity. It's a simple relationship, as in you guys could guess it almost intuitively. And this, this will be useful for some of the homework questions because the homework question will give you some material that you're looking at and ask you what is the what is the resistance of the material if you know these geometric parameters. Questions? Comment? So, this is a pretty simple law, and we are actually going to be using it a lot. For, what I'm calling simple law, we are actually going to be using Ohm's law a lot. This is one of the most important laws when you're dealing with the circuit. It's because whenever you know voltage or current of the circuit, and resistance is usually given as some constant, then it lets you figure out the other thing. I think I said at the beginning of the semester that you are going to see a lot of relationships that relate three quantities together, like ideal gas law did. This is one of those. It relates voltage, resistance, and current together, and you're going to use this a lot, the way you used to ideal gas a lot, whenever you're dealing with the circuits. Yeah.
So what I want you to spend the remaining time to talk about is some of the conceptual barriers in thinking through the answer here. I think it starts from, how do I put it? It's not necessarily useful. So I don't want to say it's useful. I think it's attractive on the face of it to think of current like cars moving along a freeway. And when you think of current that way, there is something very unintuitive about the answers to A and B and how this is shaped here. So what I'm telling you here is that on the broadest part of the conductor, where if I'm taking resistance per length, the resistance per length here might be the smallest. And I'm telling you that amount of current that crosses through this cross section at any point in time is the exact same amount of current as through the cross section here. And if you've gone the route of thinking of charges moving like cars moving on a road, then using that wrong analogy to ground your intuition, you would wrongly go into thinking that in this wider part, current flows more easily, so more current flows. And in this narrower part, current flows less easily, so current is less there. That's an easy, intuitive, conceptual mistake to make. And what I want to highlight here is that one, that's wrong. That's just not how it works at all. And what I want to offer you instead is, instead of car analogy, which happens to fail here unless you take a super careful care to set it up correctly. And I think all of that ends up being too much work. I want to give you more useful analogy that matches up much more closely to current flow. And that's what you did for the opening discussion this week, the water analogy. So I want to show you a simulation involving water flow and show you how that water analogy can help address anything that you see here that seems unintuitive. Now, so let me go to the simulation. A brief kind of explanation of why. Well, I mean, water analogy is useful, but I think I initially actually wanted to find the actual electricity simulation, and none of these simulations do what I wanted to do. So that's why I just have to go to the water analogy, because they do have a pretty good fluid dynamics simulation that does exactly what I wanted to do. It's this one called fluid pressure and flow. I think if you're in my physics 4A, you might have seen one of the lecture videos where I do use this to, I don't know, illustrate Bernoulli's principle, which technically in my physics 4A isn't a required topic, it's optional topic. So, for a bunch of different reasons, this is a good thing to revisit, see what intuition we can get out of this physical picture. And so let me go through that in the next 4 or 5 minutes. By the way, this is an interesting innovation at Fed. Java simulations, it used to be that you had to download, but I think these days you can just run it right in your browser. So, I mean, I don't think it might not run on um, every device, but at least this is a really interesting innovation. So I think it's this simulation that I had mostly in mind, although you can definitely, like with the water tower, there's a kind of lessons you can draw from here in terms of how pressure or the height difference matches the voltage. But it's the flow one that I want to talk about the most. All right, so this is the fluid flow simulation, and let's see. I guess I should tell you the elements of the analogy. So I think the physical objects are fairly obvious what they represent. These that represent, representative samples of water element, and it would represent the exact same thing in the electrical context, like a charge elements. So that's what those dots represent. So this is a visual way to represent a flow, whether it's a charge flow or water flow. And there's a way where you can measure speed, and so here the speed that they're measuring is would match up with what your textbook calls the drift velocity. I think if you're looking at your textbook, there's a place somewhere here. I think it's in this section. Drift velocity, yeah. So the reason this term is introduced is because electrons, microscopic objects, their thermal velocity is actually much higher than drift velocity. So drift velocity is kind of an average velocity moving in one direction, and that's what this speed would represent. So I think that's a kind of one-to-one thing. The place where you have to kind of match with the language of the fluid flow with electrical current flow is the ones dealing with the pressure. So I think in the fluid dynamics context, there are two different things that kind of match up with the pressure. There's a kind of something that would represent the potential energy. Like if one end of the pipe is higher than the other end, then there's a potential energy difference between here and here. And I think in the case of this simulation, the potential energy difference actually does lead to, so trying to get the bottom of each pipe, it does lead to actual pressure difference. So yeah, there's that. And that pressure difference actually does drive the, the way this simulation is set up, I don't think it actually, because it's set up to set a constant flow rate, it wouldn't actually set up, cause the fluid to flow any faster. So never mind that. But in the fluid context, I think maybe more succinct way to say this, it's the pressure difference that drives the flow of materials like this, and the electrical version, electrical analog to the pressure or pressure difference is the voltage or the voltage difference. Now, with this simulation, there is no pressure difference between one end of the pipe to the other end of the pipe. And, that is actually a real situation you can have if you have a frictionless material, if you have resistance-less material. If you have a superconductor, you actually don't need any voltage difference between the ends of the superconductor to have a persistent current setup. So there's a real thing. In this simulation, for some reason, turning on the friction does nothing. So I don't know So let's not talk about that too much. What I do want to talk about is how to connect your intuition about this kind of flow, and how different aspects of this change as you what different aspects change and what don't change as you change different parameters here. So the main parameter you can change here is the width of the pipe, and that change in the width of the pipe is what would correspond to change in the width of this conductor. And you can see in the simulation already how this narrowed pipe affects the flow of the material. And I guess I hope that this makes intuitive sense, that when this stuff flows through this narrower portion, the water flow doesn't slow down as it flows through the narrow portion. It actually speeds up. And the reason it has to speed up has to do with what the actual constraint in the flow of material here is. The constraint here is the flow rate. It's volumes per second. That's the actual constraint here. So when I have flux meter, as I move this flux meter around, it's been so this simulation has set up so that flow rate is fixed here, and I can describe it as flow rate being fixed at the entrance end. Then by the property of the water, this flow rate has to be the flow rate through any particular cross section throughout this entire length. And the property of water that's most relevant here is that it's incompressible. So I specify the flow rate in volume per second, and whatever volume of water that comes in, that's the same volume that has to leave here every second. It's this is the general property of liquid, that they don't compress that well. So however much flow is coming in, that pushes out the flow all the way down the chain, all the way out here. So that's the real constraint here. And if you think through the traffic example, that's not really the constraint that you have under most traffic circumstances, because the traffic fluid is compressible. You can have distances between cars that change quite fluidly. So the thing to be mindful here is that it's the flow rate that's kept constant. And in order to keep the flow rate the same as the cross-sectional area changes, what changes is, you know what? I have no idea how they define flux. Oh, I guess the flux is the flow rate per area. So I think rather than flux, what I think is more useful as a kind of physical thing is the speed of the particles. So in order to have the same flow rate here as here, particles simply have to move faster. That is the speed, the drift speed, the velocity v times the cross-sectional area has to be constant, so that as the cross-sectional area decreases, speed has to increase. Then you might still wonder that, like, how does that come to be? Because it feels like there has to be some other things changing as the particles move faster here. And especially if you think in microscopic terms, that's definitely correct, because the particles moving through here have more kinetic energy. They are moving faster in terms of drift velocity. And when you measure the pressure at different points, you see why. So this is entirely about fluids. So this fluid flowing kind of from midpoint to here, there's a distinct pressure difference. So it's this pressure difference that pushes the water element through, so that it's faster here. And once it's through this portion, then the pressure difference is the other way. and that serves to slow them down. And you can see a similar situation with the electrical current flow here and voltage here. So I said, referring to why the correct answer here might be unintuitive, that when you are looking at resistance per length, that resistance per length would be less here compared to here, but still the amount of electric current flow is the same. Well, if you look at the voltage change per length, what you will find that voltage change here is less per length compared to the voltage change here per length. So that when you say apply Ohm's law over that slice of the conductor, that that the current ends up being the same, because the resistance of this slice is the lower, but voltage difference across the slice is also lower compared to the resistance here and the voltage difference across that slice. And that intuition will help you as you work and think through, let's say, series circuit. Because when you have series circuit, one of the things that you have to get through early on is that the current through the entire series circuit is constant. The current through a low resistance element in a series circuit and the current through the high resistance element in a series circuit, they're the same. And the reasoning that you apply there is the exact same reasoning that applies to this one. That's why the correct conceptual understanding of this setup is useful, even as you are moving into more detailed circuit analysis. Because then when you encounter that situation with the series resistors, you don't see that as something unusual. It's something that was to be expected. So that's what I want you to talk through, and the simulation I want you to show. All right, this one looks like it requires calculations. So I'll pause it here and then answer the question. So it says, calculate the force between two charges of some amount of charge separated by some number of meters. And if you haven't read this in the chapter already, then hint will kind of take you to the section that covers it. And when you go to that, well, I'll do it just to this once. For the other ones, I'll just write down the formulas that I do know. So when you follow this link, it'll take you to section 10.2. And ideally, you should read it. That's what I recommend. You should endeavor to understand everything. But what it really comes down to is, for the purpose of that particular question, you need to know this Coulomb's law. So that's what I'm going to write down. And I need to know this constant here. And that's what I'm going to write down. So let me go back and write it down. So I'm working with Coulomb's law, which says that the electric force between two charged particles is proportional to the product of the charges divided by distance squared. And there's some constant here that we call Coulomb's constant, or the numerical value of the force constant K. I saw it, so before I forget it, let me write it down. I think it was 8.99 times 10 to 9 in the appropriate units. So this is the point of the semester where I'm going to kind of start leaning heavily on the fact that in SI unit system, the units are kind of set up so that this will have the correct units so that the force works out to be newtons. So I'm just gonna lean heavily on that and not worry about remembering all of this for now anyway. So, all right, so that's, so this is the formula that I'm working with. So I just need to plug in the numbers. So it said 0.85 coulombs each. So I put 0.85 coulombs to each of these two numbers. And then the distance that I need to plug in is 1.7 meters. And once again, what I'm trusting is that because all these are in basic SI units, that when I work out all the units, I'm going to get a unit of Newton at the end. So I could write it up, but I guess let me just
type it into calculator, just straightforward. So I'm using this on-screen calculator. Hopefully it's similar to most people's calculator. So let me just type it in. It says, oh, wait 1 second. Does it? I think, let me just test one thing. I think that EXP, okay, yeah, that's what I need. Okay, so I'm going to type in the value of K first. That's going to be 8.99. And this times 10 to the power of 9. A lot of calculators have this E notation or exponential notation. And when I press EXP and then type in 9, what this means in calculator notation is this is 8.99 times 10 to the power of 9 times 0.85, and I have one more of that, so times 0.85 divided by 1.7 squared. And this is real, actually where you might want to be familiar with how your own calculator works. I think with this on-screen calculator, I'm pretty sure if I type in 1.7 and then squared, it'll, yeah, it kind of takes precedence there. So I'm dividing by square of 1.7 and equals, this is the number I get, 2 and 2247 and then 500000. So this is where you want to watch the unit that the question asks your answer in. So when you look at the question text here, it's asking for an answer in the units of million newtons. So I know this mark is for 1,000, this mark is for 1,000,000. So I have 2,247.5 million newtons as the first. It's, as I say in the question text, it's not meant to be very realistic. Let me just pull it off to the side so that I can still see it. So 2247.5. Now, sometimes as you are doing this on your calculator, you might you might not feel very comfortable with how your calculator works. In that case, it's helpful to have something else that you can check your calculator with so that you can see what the correct answer is. The tool that I recommend for that is something called Wolfram Alpha. So the nicest thing about Wolfram Alpha is it shows you how it interpreted your input. So let me type in what it should be in Wolfram Alpha, 8.99, and then the E notation would be E9 times 0.85 times 0.85 divided by 1.7, and on a keyboard, this caret symbol, it's a shift and the number 16, that's the exponent, and I'm gonna put 2. I'm raising 1.7 to the power of 2. So when I enter that, Wolfram Alpha shows me how it interpreted my input. That's and I can kind of double check that how it interpreted my input is consistent with what it was supposed to be. So if somehow you're not getting this answer on your calculator, then this is one way you can check that if you are understanding correctly how your calculator works. I do recommend that you do become familiar with your own calculator, because on your exam, if you are taking it in person, that you won't be able to use Wolfram Alpha. I guess if you're taking online version, then this is actually allowed as long as you're using it only for calculator. So, all right, so that's the first one. I'll try to go more quickly through the remainder of these questions. Let's see. Next one, this is well, it's a conceptual question, so I'll have you work it out. Let's see. Okay, this is another numerical question. It says a test charge of something feels a force of some newtons. What is the magnitude of electric field? So hopefully you've read the chapter, you've read it through section 10.3. Oh, I guess I'm giving you the equation here. Um, it looks like it's actually telling me everything. So let me just write it out. So let me just double check. It looks like I have, I'm given the force of 5.5 newtons in basic SI units. I have force, I have charge, 9.6 times 10 to minus 6, Q. All right, so I guess for electric field, I just take the ratio. So for electric field, it's just going to be equal to 5.5 newtons, that's the unit in basic SI units, divided by 9.6 times 10 to minus 6 coulombs. And you can actually, if you wrote down the units here as what it is, newtons, then you can actually see that the units work out. Newton per coulomb, I have Newton per coulomb here. So it's going to work out. So let me do that on the calculator. Calculator. All right, let me clear this. So it's 5.5. Now, on this calculator, since I know how to use the E notation, this is what I can do. Divide by 9.6 E minus 6. Oh, wait. 1 second. I did something wrong. 5.5 divided by 9.6 E. And there's two different minus symbols. There's this minus operator, as in subtraction, and there's this one, which is a sign operator. So I can turn that into negative sign instead of plus. Complicated. All right. So that's the answer. Now, suppose you either are working with a calculator that doesn't have the E notation, or you don't know how to use it. Then you have to make sure that you use the parentheses. So that so this is a common mistake that someone could be making. You could be doing this: 5.5 divided by 9.6 times 10 to minus 7. So you do 10 raised to power of minus. Did I say 7? Oops. Wait. 10 raised to power of minus 6 minus that's what it does. 5.5 divided by 9.6 times 10 to minus 6. Now, when you look at this answer with the previous one, you can see that the answers are different. It's because this is not the same thing as what's written here. It is literally 5.5 divided by 9.6, and this times 10 to minus 6, it went into the numerator. So that's a mistake. I shouldn't have done that. In order to avoid a mistake, this is how you should do this calculation. 5.5 divided by parenthesis 9.6 times 10, and this is the button I should have pressed, because I already wrote 10, which is x, and after this button, I get to write what y is, which is minus 6, or 6 and then minus sign. All right, so that should have, So fit equal, and now I get an answer that I got before. Or if I scroll, this the first answer, which was right. So that's I guess the moral of the story here is be very familiar with how your own calculator works, so that during the exam you're not fumbling through what the order of operation is. So it's giving me 572,916, and then it's repeating. And this is another place where you have to watch out for what unit the question is asking for your answer in. So if it was just asking for answer in Newton per coulomb, then that's what I would put in, and that would be correct. But here, the unit that the question is being asked in is not Newton per coulomb. It's in million Newton per coulomb. So there are different ways to get, okay, so what do I need to put into this box here? I think the easiest way as long as you have the calculator, is to divide this 10 to the 6. Or what you can imagine is, so you have that answer there, 57291. I'm going to round it here, 917. And this answer is in Newton per coulomb. And what you really need to do is you need to convert this into this unit, 10 to the 6 Newton per coulomb. So what you are really doing is multiply by, I guess, so on the numerator, I want 10 to 6 Newton per coulomb. And if I'm just multiplying by that, then I'm changing my number, and I don't want that. So I really want to be multiplying by 1, which means a quantity where the numerator and the denominator has same physical value. Here, so the same physical value happens to be just 10 to the 6 times Newton per coulomb. I mean, it's the same thing as what's on the numerator. I just wrote it out this way so that you can see that Newton per coulomb cancels out. So on the numerator, I'll have this. That means numerically what I have to do is take this number and divide it by 10 to the power of 6. So let me do that here, and that'll give me a number I can plug in. So take the number, divide it by 10 raised to power of 6. All right, so I get 0.573. Let me plug that in, 0.573, and that should be the correct answer. All right, let's keep going. Let's see, here's another question that's asking me to do numerical calculation, which is probably going to involve scientific notation. So it says an experimental apparatus set up with electric field. Here, it's giving you the unit in volts per meter, because I think depending on where you are in the reading, you might not have seen volts per meter, and that could confuse you. That's why I'm saying it's the same as Newton per coulomb. And if you work out the units, volt per meter is the same as Newton per coulomb. So if an electron is released within this electric field, what are the magnitudes of the force on the electron and its acceleration? All right, so I have, this is my electric field. And if you look at the hint, then it says, oh, remember that force is, it's actually the same expression that you just saw earlier. It's now solved for force. So the force is equal to charge. And the question is actually telling you what the electron charge is so that you don't have to look up. You can actually look this up on Wolfram Alpha, by the way. So in Wolfram Alpha, if you look up something like electron charge, it'll tell you electron charge is, there it is, minus 1.6 times 10 to minus 90. But in this question, since I'm given that, let me just use that. So the electric force on the electron is that amount of charge, 1.602 times 10 to minus 19. And I'm just going to trust the units will work out, so I won't write it down. Times the electric field is equal to 2.3 times 10 to the 6. And I'm going to trust that units will work out. All right, so for the force, let me multiply that out and see what I get. I'll use the calculator here. So I have 1.602, and I'm just going to use the notation. That's the quickest way to put in the scientific notation. Minus 19 times 2.3 E6. All right, so I get that. So whatever it is, one thing, let me copy it down so that I not this. So how many zeros? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 zeros after the decimal. 3, 6, 8, 4, 6. Now, if you were to put this in here, it would tell you that that answer is wrong. It's because this is a unit of newtons. But what the question is asking for is in the units of piconewtons. So you need to convert newtons into piconewtons. This is where you kind of need to begin to know the metric prefixes or SI prefixes. And if you don't remember what pico stands for, this is where you can find it. When you go to the textbook has a section called useful information. It's at the very end. I think it might have been linked from something earlier. When you look at useful information, it has a bunch of tables that should be helpful to people who are trying to remember some numbers and pieces of information. And one of the tables is the metric prefixes. So it has all these, and there it is, pico. The pico means 10 to the power of minus 12. So I need to convert this number here into, which is in units of newtons, into piconewtons. So I'm basically doing unit conversion that was covered way earlier in the semester. So I'm multiplying this by 1. So on the numerator, I want piconewtons. So I want this to be 1 piconewton. And according to the table that I looked up, 1 piconewton should be 10 to the power of minus 12 newtons. So that's what I'm multiplying this number by, which means going back to the calculator, I guess I need to be dividing by 10 to the power of minus 12. So let me do that. Divided by, one way to express 10 to the power of minus 12 is 1 exponent minus 12. It's 1 times 10 to the power of minus 12. So when you do that, you get 0.368. 3 significant figures are enough, so let me do that, 0.368. So here you don't actually have to use any scientific notation, but you do kind of need to understand that background with the powers of 10. All right, so that's one, and it's asking for its acceleration. So the hint doesn't say, but this is where you really have to remember the material from your exam 1, that net force is equal to mass times acceleration. And here, the electric force is the only force, which means acceleration is the electric force up there divided by mass. So I guess I will write that out on the calculator. I think I already have the force. Well, in units of piconewtons. So let me put that piconewton thing back. 1e minus 12. Okay, so piconewton is back in. It's back to the newtons. So now I can do what I can do is take this force and divide out the mass of the electron to get the acceleration of the electron. So divide this number by 9.11 times 10 to minus 31 equals. All right, this big number, I'm not going to read out the whole thing. Now, I'm kind of actually happy to see that big number, because looking ahead, so if I was just answering it in meters per second squared, then great. I do that, get the number, put the number in, and I'm all done. What the extra step you need to take here is this metric prefix, or the power of 10 that you have to deal with, 10 to the power of 15. So you are converting from units of meters per second, that's the unit these numbers are in, to unit of, you can kind of treat this as a unit, 10 to the 15 meter per second squared. So one way to get what should be going on here is to just divide 10 to the power of 15. So let me do that. So I have divided by 10 to the power of 15. That gets me 404 times 10 to the power of 15. Okay, so let me put in 404, and I should be done. Let's check. So clicking submit. All right, that's it. So this is really the something that if is depending on the degree of how much you have forgotten it from your math classes, this is what you need to review so that you can one, do these questions on your homework. But if it's only on homework, then I would just tell you use Wolfram Alpha because it really does make your job easier. But because you might see some of this on your exam as well, especially for those of you taking exam in person, I recommend that you try work it out using your calculator that you can use during the exam. All right, let's keep going. Question 9, 10. I thought there was one more numerical. Question 11. I guess this is probably an experimental apparatus is set up with a voltage difference of something. I guess that's probably going to be relevant. I guess this is where you kind of have to know some of, let me just keep on reading. So that's the voltage difference. If an electron moves from the positively charged electrode to the negatively charged electrode, how much energy does the electron gain in joules and electron volts? I guess calculation-wise, joules are actually not easier, but concept-wise, it's easier. Because with the joules, you can kind of, it is a standard SI unit of energy. So if you have, so this is the expression that I was half remembering there, that change in potential energy from change in electric potential is equal to the charge of the test charge. Or in this case, I guess it would be the electron times the change in the electric potential. Here there's a bit of a sign issue because the charge of the electron is actually negative. So yeah, so in joules, it's simpler in this sense. If I plug in charge in coulombs and the voltage or electric potential change in volts, then all the units will work out. I'll get the unit of joules for the change in potential energy, or how much it's the energy that the electron gains as it accelerates between the electrons. So, yeah, I guess I'll just do the calculation. So I hope some of these numbers are in the hints, so I don't have to look it up separately. Oh yeah, it's giving me the electron charge. So let me just plug in the numbers. I'm gonna ignore the sign here because electron gains, that language is gonna take care of all the signs. So then let me do this. So I'm gonna just ignore the signs. So the amount of charge, the elementary charge or the magnitude of the charge of the electron is 1.602. The E notation minus 19. That's the charge, and you multiply it by the amount of volts, which is 37 kilovolts or 37,000. So 37 and 3 zeros equals, this is some number of zeros. Let me not write that all out. All I need is the fact that the question is asking for the answer, the blank, in terms of the unit of picojoule. So we looked it up just now. Pico means 10 to minus 12. So here to convert this joule number into picojoules, then I want to be dividing by 10 to minus 12. Let me just double check that's what pico is. Yeah, 10 to minus 12. All right, so then divide by, I'm gonna use the E notation again. So 10 to minus 12. All right, so that's the answer in picojoules. So it's still got some zeros left, 0.00593. So that should be it, 0.00593. And we'll see if that's correct when we put in the numbers. So electron gains that much energy, or in other words, this is where calculationally, actually, this is easier. But conceptually, I've seen people take longer to kind of grasp what we mean by the unit of electron volt. And actually, when you write it this way, it's a little bit clear what electron volt means. it really means this. It means it's a unit of energy, but the way the baseline is established is you calculate it for one elementary charge of the proton or charge of the electron. So that's equal to 1E, where E stands for this, times the change in voltage. So 37 kilovolts, or that's going to be equal to 37 times 10 to the 3 volt. Volt. So when you plug in these numbers, then you get the how much the energy the electron gained in electron volts. But looking at this, I hope you realize that you don't actually really have to calculate any number. And this unit of electron volts, or EV, it really works out to be it's a multiplication of E, the elementary charge, and volt, the electric potential difference. So when you do this multiplication, E together with the volts are going to give you electron volts. So I only really need to worry about this number, 37 times 10 to the 3, which was the amount of voltage difference. So so that's going to be the answer here in terms of electron volts. And I guess, well, the question is still telling me how to answer the E notation. So let me just painfully type this out. It's 37,000 electron volts. So 3 zeros. All right, that should be it. Let's see. Yeah, that's it. Hopefully that's relatively clear. Let me look at question 12. All right, so that's all the questions on this set that requires calculation. All right, question 4 looks like it has some calculation. It says help you develop some intuition. All right. It says a typical small electric device is powered by a battery whose resistance can change to get a sense of amount of calculate amount of current flowing through a resistor of 6K ohm powered by a battery of voltage of 4.4. I like to draw the physical setup even when I'm not really using it all that much. So I can think of it as being powered by a battery over a few volts. The question tells me it's going to be 4.4 volts. And the way we are modeling how much electric power is, or how much electricity is used, the small electronic device, I think I can model that with basically a resistor as a circuit element. So what you have is a 4.4 volt battery connected to this resistor, which is kind of simulating your typical small electronic device. And say that, I'm giving the resistance of 6 kilo ohm. Or what 6 kilo ohm is 6,000 ohm. All right, so it's asking for the current. This is where you kind of have to remember Ohm's law, and I'm pretty sure that's sort of what I'm telling you in the hint. Review Ohm's law. So, well, and I guess it actually gives me this equation. So I guess I can just use them. The current, that's what it's asking for, is the voltage divided by the R. Here, R would be this internal resistance. All right, so let me write this out. So I have the current is equal to voltage, which would be 4.4 volts, divided by R, resistance. I should be able to get the current that's flowing through this circuit. So the resistance is 6 kilo ohm, or just writing it in basic SI units, 6,000 ohm. All right, let me do that in the calculator. I don't need any scientific notation for that unless I really want to use it. 4.4 divided by 6,000. So now this is what I get, 7.3333, and I don't want you to stop there. I want you to see this times 10 to the power of minus 4. So this is the correct answer if my answer is supposed to be in the unit of ampere. But I am dealing in the unit of milliampere. And if you have forgotten, in the useful information, you can see that milli stands for 10 to the power of minus 3. So what I'm going to do is, all right, so I have this value of current in amperes, and I need to express that in milliamperes. So let me write this out, 7.33, so that's in ampere, or times 10 to minus 4, that is in amperes. And you want to convert this unit to milliamperes, so milliamperes. You think through, okay, what other unit is equivalent to this, and that's going to be ampere, and that works out nicely because this ampere will cancel out that ampere. And I guess the way I should write is 1 ampere is equal to what's going to be on the numerator, 1,000 milliampere. And here I can actually do this particular calculation by hand, especially now that I have this 7.33 already. Let me show you this as a kind of a illustration / reminder of the exponent algebra that you might have learned. So this 1,000 milliampere can be expressed as 10 to the power of 3. And the way you do this calculation is quite simple if you know what you're doing. So let me go through step by step of assuming I'm someone who knows what they're doing. Let me just go through step by step. On a multiplication like this, what you really want to do is you want to separate the two parts. So you do the calculation based on these leading numbers first, 7.33 divided by 1. And then later on, you work out what this exponent would be, 10 to minus 4 times 10 to the 3. So when you work out that multiplication of the two values, then this is what you should get. 10 to minus 4 times 10 to the 3. And this is the exponent algebra rule. These are two of the some of the common rules that you see. If you have a raised to the power of x times a to the power of y, in a case like this, you can simplify this to say a to the power of x plus y. And you could prove this using math, but in the interest of time, we'll say that you accept that to be true. Then what you need to do is I have this 7.33 times all these powers of 10. So let me simplify this first. All these powers of 10, they become 10 to minus 1. So multiply that with 7.33, I get 0.733 milliampere. So that should be the amount of current. All right, clear all drawings. 100-watt light bulb operates on household line of some voltage. And while it's on, it has effective resistance of some resistance. It says calculate the amount of current flowing through the 100-watt light bulb while it is on. And this is something you are going to read in the chapter, that there's a power dissipated by a circuit. And the power in an electric circuit is given by current times voltage. So we are given the volt, and even though we are given the resistance, I don't think we need to use it because in this expression for power, I have something that I can solve for I, the current. The current is power divided by the voltage. So I guess we'll try that. I think I can do this on my calculator. So I'm going to say So the power here is just 100. That's the rating of the light bulb divided by voltage. That's the 110 volts. So divided by 110. So 0.91 or 0.909. All right, let's see. All right, that was correct. Finally, for long segment of wire, it is not unusual to have a resistance as large. Yeah, 1 ohm is pretty large resistance for a wire. Remember, ideally wires have zero resistance. To get a sense of the change of voltage, voltage change across. I'm looking for voltage change. All right, I think I have all the units. So one thing that you should know about voltage change, the change in the voltage across the wire is going to be the current through the wire times the resistance of the wire. It's a version of Ohm's law, or it is Ohm's law. So you say that is equal to, I have the current of 6.5 amperes times the resistance of 0.8 ohm. So voltage change across wire is, well, I guess I just multiply this out. And here I have both amperes and ohm. So I have that promise in the SI unit system that 1 ampere times 1 ohm is going to give me 1 volt. So, I mean, let's hope that's the case. So I'm going to put in 6.5 times 0.8. So the voltage change should be 5.2 volts. All right. Okay. So all right. So that's all correct. I guess with the circuit, right? With the circuits, there aren't that many questions that require you to do scientific notation. I mean, there are questions that require you to calculate, but not that many. So that's mainly because I think when you go from static electricity to circuits, a lot of standard units become something sensible. Like a small AA battery has voltage of 1.5 volts. Doesn't have voltage of 10 to the minus 19 volts. Let me just look at the other two questions. I guess, I have to do 1, 2, 3 questions, and not that much time. So let me just quickly go through it. This time I'll just write things out without going too deeply into physics. Read the textbook, read the chapters, and that'll help you understand. So, okay, the typical power rating of microwave is about 1,000 watt. How much current microwave oven rating of 1,200 watt draws while it's on? Okay, so I think the way it's worded, I don't really need to care about 1,000 watt. I don't care at all, because the question is asking me about a microwave oven that has 1,200 watt. So how much current? All right, so I think I have some sense of what formula I need. I need the formula for power. So I am using power is the current times voltage. But what I'm going to change is, because the question is asking for current of, so I really need to have this solved for current. So I can imagine multiplying both sides by 1 over V. Then what you end up with is current is equal to the power that you are looking for divided by voltage. So, ratio. So, all right, I guess I'll just plug in the numbers. So I have, for power, it's gonna be 1,200 watt, and voltage, if it's same as regular household, then that's 110 volts. So divide by 110, you get 10.9 ampere. That's actually a fairly large amount of current if you are dealing with electronics, or it's a fairly large value. Let's see. I guess I'll do B. I won't say too much. I'll just just to write down what it should be. So typical value at low amperage is, so this 15 ampere is the current that I'm going to be dealing with. How much power can be drawn for any wall socket? So wall socket means the voltage is equal to 110 volts. I don't know if I need to change anything. And the power, I had a formula before. Power is equal to current times voltage, and you can read more in the chapter section about where that comes from. So I guess I just plug in the numbers. So plugging in the numbers, it's the current, 15 times the voltage, 110, 1650. So that should be the number of watts. So 1650 watt. Last one here on electrostatics may use while it's on. Wait, did I already do this? Yeah, we did this already, kinda in part A. So yeah, so yeah, so let me just. I don't need to do that one. For part C, look at part A. The only thing that's changed is the number for the power usage. So I have two more questions left. Let's see. Household electric power is usually billed in units of cents per kilowatt hour. How many joules is 1 kilowatt hour? All right. I guess I should do this unit conversion. I think it's gonna be instructive. By the way, you can also do this. Wolfram alpha is unit aware. So if you say 1 kilowatt hour in joules, it'll actually be able to tell you what that is. It tells you how it interpreted your input, and it gives you the answer. And that's gonna be the correct answer, but let's go through that so that we know how to do this by hand. So let me start by writing out this 1 kilowatt hour. So 1 kilo, that's gonna be times 10 to the 3 watt times hour. And this is where your knowledge of the interrelationship between units is important. So if you know that 1 watt, which is unit of power, is related to energy by change in energy per time, or that 1 watt should be 1 joule per second, then that'll help you work out what this watt times hour is. This is the unit of power times unit of time. So that, oh yeah, when you do the unit of something like 1 second, then you can see on the right hand side the second cancels out and you get the unit of energy back. So here, this is already fairly close. I already have watt. I don't want to change that. So what I really need to change is the hour. Instead of this being hour, I need that to be 1 second, so that I can say watt times a second is joule. So so this is how you convert to unit. Once again, you multiply by a factor of 1. So here, my factor of 1 looks like this. On the denominator, I want hour. So let me put 1 hour. This is so that hours will cancel out. But if I just randomly start multiplying by numbers, that changes my number. So I want to be multiplying by fraction, where the numerator is the same as the denominator, same physical quantity as denominator. So 1 hour is 60 minutes. And I can, but minute isn't what I want seconds. So let me do this one more time. So I want to cancel out the minutes, and 1 minute is 60 seconds. Okay, now I think I have everything. So if I take this, multiply it by 60 times 60, that'll give me watt times a second, which is joule. Okay, so let me do that on my calculator. So it's gonna be 1,000, so or 10 to the power of 3, or 1,000 times 60 times 60 is equal to some big number, 360 and then 5 zeros joules. And I guess that's the unit it's asking for, so I'll just type that in. 36 and then 5 zeros. 1, 2, 1, 2, 3. So that should be it. All right, so that's a unit conversion. We did cover that like in chapter 1 or 2, but it's good to review. You'll see more of that. Question 7. Yeah, I should do this one. I remember getting question about this one in the previous semester, so I should do it. So this question gives you all the information. I think a hint kind of tells you. So the one thing you do have to know, which is why I give that to you in the hint, is that you have to know that a AA battery has provides a voltage of 1.5 volts. You kind of just have to know that. If you don't, that's why I give that to you in the hint. That what I do is, okay, so it's asking me how much energy. So from the previous question, I know that amount of energy can be expressed as amount of power per some duration of time. And this power, from having read through the chapter section and everything, I know that power, electric power, is equal to current times voltage. And so the amount of energy stored in the battery should be, so I'm just going to flip this around so that at the voltage that the battery provides, it should be amount of current it's able to provide at any given moment over what the duration of that, over how long a duration the battery can provide that amount of current. And that's actually written into this unit of 24 or unit of milliamp hours, or so milliamp hours, it only means is milliampere times hours. So really all we have to do is I want to convert these hours into seconds. I want milliampere expressed in terms of ampere, and and I need to multiply by voltage. So so let me kind of write this out. So the amount of energy that's stored in the battery is going to be equal to the voltage, 1.5 volts times the current. I'm just going to say it's going to be providing current of 2400 milliamps, or let me make it a little bit easier for myself. Or that's a 2.4 ampere. 2.4 ampere times the duration of time. So for this milliamp hours, if I'm getting 2.4 amperes, then it will last exactly 1 hour. Or you can do the unit conversion, same thing that we did just now. And when you do that, you will see that this is 3600 seconds, or 60 times 60. So multiply all this out, and these are all basic SI units: volt, ampere, seconds. So your final unit here should work out to be joule. So all I need to do is just to work out the numbers in a calculator. 1.5 times 2.4 times 3600. So it stores energy of 12,960 joules. So 12,960 joules. So let's put that in, make sure that it's the correct answer. The typical AA battery stores 12,960 joules. So I think that's all the calculation questions. Hopefully this is a kind of a good review, reminder, practice. I did all the calculation questions. So as you're doing it, so your numbers will be different, but you can kind of follow along in this video, or bring this video up in the correct part, or the one that's handling the same question, and follow the same approach if you feel lost anywhere.